Okay, so far we've done the following. So we've defined a factorization category I goes to rep G check I, and another factorization category I goes to sf. So I still have to explain how I manipulate with these infinite dimensional gadgets. I'll postpone it till the end because I don't want to do two very technical things, well, back to back. So this formal disk stuff was nightmarish enough. So, well, this was, G of k modulo G of O modulo G of O. I had to justify how to manipulate such things. So I'll postpone it till the end. Maybe I'll postpone it even further. Well, it's written in the notes for. If you download the notes for. Pardon? Either Sam's talk this morning or my lecture on day 4. So on Kac-Moody lecture, it's written there. But okay, but it will be presented as well. Anyways, so here are two more things that I want to cover. So one is to extend the naive Satake to a homomorphism of monoidal factorization categories. This is one thing, and the other thing is I want to state the compatibility of the naive Satake with our conjectural geometric Langlands. So these are the two things that I want to accomplish in this hour. Okay, so to talk about the former, so let's talk about this category a little bit. So here is how it was defined. So from the previous hour, recall that rep G check I was defined as quasi-co of this jets horizontal into BG check times x deram. So this is, if you wish, incarnation 1. It's definition, but there are two more incarnations. So the second one will be less handy, but also important. So, and it was mentioned by Sam. I will not prove the equivalence of all three, although it's not very difficult. So Sam explained that if you have M symmetric monoidal category, it gives rise to a factorization category, let me call it C sub M, and moreover, it's not just factorization category, it is a symmetric monoidal factorization category. So each of your CIs has a symmetric monoidal structure, and these factorization equivalences that are compatible with the symmetric monoidal structure. And so now, and pardon me?
Is it different than
what?
Is it true that you have a symmetric monoidal factorization category and it comes?
Almost. If you have a symmetric monoidal factorization category, it comes a unique way from a symmetric monoidal category, a sheaf of symmetric monoidal categories over x deram. So it doesn't have to be constant, but it comes from the curve.
As with algebra.
As with algebras, it's completely true. And yet there is one more description of this, which is kind of very, very down to earth, and it's the most handy one for some purposes. Let me explain what it is. So let me explain what this category. Third description. Let me explain what it is for the finite set 1, 2. So I'll say very concretely. So this is the following things. These are D modules on x times x equipped with an action of G check by automorphisms such that on x times x without the diagonal, this action is extended to an action of G times G. G check times G check, extended by means of the diagonal map. And this is what you do for an arbitrary power. Like if you have n distinct points, you have n copies of the group acting.
You're reading an I on the right side. From the left order. Jet is X. One jet's I. The third row. I actually don't understand. Suppose I have not 2 points but 1 point. Why?
It's
Can you explain why it's the same?
yeah. So if you do jets horizontal BG check X 1. Well, it doesn't matter what BG check is. If it's an arbitrary Y, it will be just BG check time X de Rham. If you read the definition, just give that. Jets into anything, the first term is that something. Okay?
You're saying that on just first power of the curve, your category is just d modules with action on GG.
You said that yourself, right? If you take jets, horizontal jets into something on the first part of the curve, you recover that something.
Yeah.
So you take quasi-coherent sheaves on that, it's d modules on X with an action of G check.
It's horizontal.
Horizontal, yes, it's horizontal. So this third description is very handy because it says that rep G check has a T structure and it's unique T structure compatible with the forgetful map to D modules, and moreover the same story goes through. Take the heart, the canonical map to rep G check I is an equivalence. So X equipped with an action of G check. What I mean is quasi-co on BG check times X de Rham. That's definition. Yeah. Yeah, but coherently it means that. Such that when you restrict to the square of the curve, this action can be extended to G times G. Okay? And so using this, you can, so let me just say that there is construction. So Satake naive extends to a map Satake naive I from rep G check I to SFA. So there is something to do here, but I claim that from the third description of the category, you will be able to define this naive Satake as a factorizable functor between factorization categories. And it's actually performed somewhere. So in my paper on de Jong's conjecture, it's carried out. It's kind of it's a billion. Yeah. So the way you do it, you construct a functor from the abelian category to the abelian category, and then you apply this universal property of the derived category. So you carry this construction out to the level of abelian categories. Well, Satake was kind of started life at the abelian level, and you basically have no kind of escape. You have to kind of do everything at the abelian level. Okay, so this is part one. So this is Satake. So now I want to explain the compatibility of the conjectural geometric Langlands equivalence with Satake, and that's another story. So I'll first do it at a point, and then it's more fun to do it with moving points. So fix again the point of the curve. So what I want to do, I want to come back to my spherical category in one point, and I want to explain that it acts on the category of D modulus on bun G. Okay, let's do it. So, and again, I'll cheat using this infinite dimensional gadgets. So we introduced another space. I'll call it bun G level X. So this is the modulus stack. So classifying G bundles equipped G bundles on X with trivialization on dx. So dx, this scheme maps into your curve, and you can restrict your bundle and equip with the trivialization. So this is called bundles with a level structure. Now, there is a have the forgetful map. And so by construction, it's a torsor with respect to the group G of OX. So it acts by changes of the trivialization. And the basic fact here is that the action of this group extends to the action of the loop group. So this extension is due to this Bourvil-Laszlo theorem that you can, it's the regluing procedure. So and now using this, I'll define this action by the following diagram. So I'll write G of Kx times bun G level X, G of OX, G of OX. This will go to bun G as follows. So you act, and then you divide by G of OX. So this is a map to bun G. And here you'll go to G of Kx modulo G of OX modulo G of OX times bun G. Again, I'm using all the time that bun G level divided by G of OX is bun G. And again, your monoidal operation is, your action is pull, push. Yeah. Yeah, so bun G level divided by G of X is bun G. And again, this diagram defines you the action. So I don't want to drag you through this procedure with formal disks again, but if you observe carefully the definitions, so I claim that there is an action, so action of spherical GI on the category of D modules on X to the I times bun G. So you can do everything relative in families, and so, well, you'll have to define this relative version of the formal bun G with trivialization, again, on this formal disk. And again, so I gave you the tools to do this. You do these jets constructions. And just mimicking this, you will obtain an action like so. So this was, okay, you have this part structure. So now, yes?
When we want to do that, we just have to ignore that we don't know what D modules on Kx are.
Yeah, well, so far we kind of, yeah, so take this as, you're taking this for as a black box, and I'll come back to it.
We want to work out that example, we have to do that.
Even this example, yeah. And in fact, I think I will have time to do it, so. Okay, so let me explain what I'll do now. So the next thing that I'll do, I'll define an action of this on I'll explain that this category acts on this tensor product. So again, as was mentioned several times, D modules on the product of two sufficiently reasonable things is the tensor product of the D module categories. So I could have as well written it as D mod on xi times D mod on 1g. So once I have accomplished the construction of this, let me just state the compatibility. So conjecture, it's so enhancement of geometric Langlands. So it says that the geometric Langlands equivalence, which is an equivalence here, let me call it, is compatible with the naive Satake. So what it says is that these actions are compatible. So these diagrams commute for every I in the way compatible with restrictions, not factorization, but just restrictions between finite sets and under surjections. So this is the formulation of the compatibility.
Can you say one more time how rep G check acts?
I know it's more complicated. I'll spend the next few minutes explaining that. So kind of I will say what it is. After I will have said that, it makes sense as this conjecture. So the conjecture says that the action of this on this is compatible. Sorry, it's naive Satake. Is compatible with an action of this via this naive Satake. So now I want to explain this action. To explain it, we note the following, that if you have any pre-stack y, you have quasi-co of y acting on int-co y. So the first thing you have to do it for schemes. So, and again, I think I mentioned it already. So for a scheme S, you have perfect complexes acting on coherent complexes. You can tensor anything coherent with anything perfect. You'll get something coherent. This leads to an action of quasi-coherent sheaves on int-coherent sheaves. And this is compatible with star pullbacks along the quasi-coherent side and shriek pullbacks along the int-coherent side, leading to an action of quasi-coherent y on int-coherent y. So in light of this, in order to define this action, it will suffice for me to construct a functor. So we'll construct a monoidal functor from rep G check I to, well, this tensor product, D modules on xi times, so G modules on xi times quasi-coherent sheaves on local systems. To do this, I'll, well, recall what D modules are. These themselves were quasi-coherent sheaves on the de Rham space. So it will be quasi-coherent sheaves on x de Rham times log sys G check. So I want to construct to the I. So I want to construct this monoidal functor. So let me first do it again over the point, in which case it will be easy. So first, fix a point x in the curve, and we'll construct a functor from just rep G check to quasi-coherent sheaves on log sys G check. And this functor will have a name. Well, I call it evaluation functor. And, well, it's very easy to construct, namely, well, it's just pullback. So I claim that local system check, given any point, maps to BG. check. So you can restrict your local system to a point and get a G-check torsor. And this functor is just pulled back. So, but this is kind of deceptively too simple when you have a single point. So to give this construction in general, we'll have to, well, that's why I went through all this procedure of jets. We'll need this full force of these jets to give this construction in general. And this is something that I'll explain now. So in general, this functor, so let's recall again that is quasi-co of jets horizontal BG check times x dram I. So this functor will also be given by pullback. So I claim that there is a canonical map from x dram I times log sys G check to jets horizontal Okay, so let's make a final effort and define this map. All right. So I need to define a map between prestacks, which means that for any S point of this, I need to define an S point of this. So let's decipher it. So I give myself an S point of this thing. So what, in other words, what do I give myself? I give a map from S reduced, call it xi, to x to the I. And I give myself a map S times... Sash, ты очень сильно мешаешь. If you want to ask a question, ask me.
I can ask a question, but you won't be happy about it.
Okay, go for it. Yeah.
So my question is, if you use the third description of
Yeah.
your factorization category, why isn't it obvious how to construct this?
Go for it. Yeah. Come.
It's so obvious that, yeah, why can't you just repeat what you said at one point, literally? Changing any condition, but just write x to the I everywhere.
It's tutorial, it's open discussion, come.
Okay. So, well, I'll definitely get confused, but let me try to somehow.
Yeah, do 2 points.
So we have this log sys, how do you know this? G-check.
Yeah.
And times x to the I.
Yeah.
So,
So I want a sheaf on that, right? X to the I dram. I want to get a quasi...
yes, I mean, I just want the sheaf on this, which is sort of is a D module in the x to the I
Sure,
direction.
yeah.
So,
Starting from the datum of this, you know, this guy with 1 action and away from the diagonal with 2 actions.
but the question is, don't you have this from the very beginning? I mean, if you have, I mean, you use this when you define this evaluation. You use some kind of universal thing, which is so what you have is that you have some object which lives on this, right? Which is just this. You have a sort of principal G-check bundle over this thing with a connection along X.
Yeah.
And then you sort of, from that given representation of G-check, you produce, well, I mean, I have to think how to say it, but what I mean, definitely, if you have, okay, I mean, I can.
It's hard to say it. I mean, so basically, kind of.
I think it should be. I should think.
Dim, is it obvious to you?
Dima says that it should be obvious.
Well,
But this is
this is exactly what I'm doing. So I'm going through the formal disks. So basically, Sasha, what I claim that you can't do this construction if you unless you really fuse formal disks.
okay, let me think.
Yeah, I would be very happy if you could do it, but it's not clear to me how.
So if you just take the tensor product over I of pulp X, it's not the right object.
No, because the category is it's tensor product over. See, the category changes when the points collide. So maybe it's possible. Okay, so maybe actually it's possible to do using the second description. That's better. So I can. Okay, I'll do it later using the second description. So that we can do. Okay, so let me just finish this because it's. Okay. Sash, let me just do this and then we'll do it, okay? So having a point, S point of this is the data that I wrote. Now we want to produce a point of this thing. So that's what we have. And here's what we want. So what we want is a map from this dxi deram over S deram with S to BG check. But I claim that by the very definition, this maps to this. There's a forgetful map. And so what you do, you just compose. Okay, so let me try to do what Sasha wanted to do. Let's do it of the second power of the curve, but using kind of this second description. So what did Sam give us?
You're using the fact that both the thing upstairs and downstairs are internal home, right?
Yeah, and I'm saying that what the internal home from maps, one maps to the other. The formal disk maps back to the curve. Okay, so let's recall Sam's description, and it was the following. So we took rep g check well, times rep g check abstractly as a category. Okay, it's rather like this. It'll be rep g check tensor d mod x squared. So here we had rep g check times d mod. The functor was identity tensor deram lower star, and here we had the push out. So had rep g check times d rep g check times d modules on x. So this was tensor product times identity, and our category here was the push out. So this is rep g check 1, 2. So we want a functor out of here to d modules on log sys. So a functor out of push out is a compatible family out of the terms. So let's try to do it. So indeed, as Sasha is saying, that we can do it along each. Indeed, it seems to work. So you have rep g check. Well, yeah, it does. It does seem to work. Yeah, yeah.
I want to say, but in what sense, in some sense this is pretty close to the third approach, but you have to figure out in what sense you glue things on the complement of the diagonal with what goes on the diagonal. So I believe that this, maybe I'm trying to promote my talk about the gluing of the.
Okay, so this is the second approach, and indeed that gives the functor. Sasha, you win. Replace 2 by 3. Okay, so.
No, but actually maybe something different, but maybe something can explain because I really can't figure it out.
Yeah.
So I want to say that somehow when you just on
Yeah.
We're kind of using the fact that local system is really modular space of something. You're using the universal object.
Yeah.
The universal local system. So somehow, is it possible kind of geometrically say what replaces it when you have the second part of the curve? And when the points are distinct, you just want to take the product of these points. And then that's how on the day. So, I mean, what I'm asking, is there some kind of just purely geometric object?
Yes.
Which leaves.
Okay, so because you did so well on this, I'll give you your desired geometric object. No. So here is what it is. So take x to the I times log cis. You check. On it, you have the following universal guy. So there exists, let me call it reg g check I. So it will be an object in this category. And it looks as follows. So if you take distinct points of the curve, it will be like I times the regular representation twisted by a local system. And then what you can do, you can and then you can construct the functor as follows. So you take reg g check I, well, tensor with the object of your category and take invariance.
This is an algebra in your category, and then
it's a factorization algebra.
But no, this I understand. But I'm asking: was it possible to construct a geometric object somehow without constructing first this check I? Can I just, I mean, say geometrically what this thing is without using any factorization structure or reg check or whatever?
But it'll be an object of what?
It's just a G-check principal G-check bundle with a connection along X to the I.
No, principal G-check bundle exists only on log cis.
Sorry, not principal G-check bundle. Sorry, it's some scheme mapping to or in the scheme of pre-stack whatever mapping to X to the I times log G-check, such that it has the structure which you had in the first description. So away from the diagonal it has an action of G-check or G-check, and on the diagonal.
My dear, this is the jets. Jets horizontal into BG check times X derum is that.
Well,
so
what I'm asking was whether there was an elementary construction of that.
No, I don't know the elementary construction. So you've got this guy.
This I understand, but that's more, I wanted to.
Could you say so you have?
In fact, not BG check. Sorry, it's G check.
You have over the run space you can define a space where over every n tuple of points
You have a G.
No, you just take the formal disk, the union of the formal disk over these points, and that will all glue into a family, and you can kind of make it DG along the.
But this is what we've done.
I mean, paraphrasing what you said before, my question is whether it's possible to construct it without using formal disks.
Okay, so you want to construct this version of G check over X to the I. That kind of when this points are distinct, it's n copies of G check, and there's one point, it's one copy of G check. No, that's what these formal disks are for. So to do this thing, you exactly need the formal disks. So kind of just forget G, it has nothing to do with Z. Take arbitrary target Z. So you start with the abstract scheme Z, you want to construct something that lives over X squared, such that away from the diagonal is Z times Z, and over the diagonal is Z. So I don't know how to do it except using formal disks. Remember what you're explaining?
I'm saying that this is not an object of classical geometry, because there's nothing.
Well, if Z was affine, it'll be an affine scheme.
I mean, I want
Of infinite type. Yeah?
so it looks like the object you define in the beginning of your notes to that workshop. Do you remember?
All right, so that was it. So again, Sash, say it.
No, but so here G was fine dimensional. Fine.
Here, yes. But even if you start with something finite dimensional, when you construct this thing over x to the I, it's of infinite type, although over every fiber is of finite type. All right, so we're done with Hecke. So we introduced the spherical, we introduced rep. Both sides acted on the corresponding sides of Langlands correspondence, and now we enhance the conjecture by asking that it commute with naive Satake. Okay, so now the thing that remains to be done is to develop this infinite dimensional geometry. So what? Yes.
Question, just suppose that you prove this conjecture.
Yeah.
That in principle, in conformity to stronger conjecture, that secret is also derived Satake, as you mentioned, and you can require that this thing commutes with derived Satake.
Yes.
So will it automatically follow or not? The fact that there's an equivalence which commutes with naive Satake, will it automatically commute with derived Satake, or is it a separate statement?
It is a separate statement.
Can I ask you something?
Yeah.
So there is a saying that the Satake is like Langlands. What precise sense?
No precise sense. So Satake is an equivalence between acting objects. So just geometric Langlands is the equivalence of something, and some other things act on them. And this particular version of Satake is really in the equivalence of acting objects. So Sam, maybe you can do this infinite dimensional geometry? Can you? Because I'm out of energy. So can you do also the equivariant story? Yeah, just do it.
So what do you want? You want Placid schemes? You want
No, you don't need D modules. No Placid. So
just definition.
D modules and push star performance for morphisms of finite type.
Okay.
With the presence of something not acting, like not in group, just group, just geo group.
Okay. You mean? Meaning you want equivariant categories for infinite type or something? Okay. So maybe there are only so many new definitions of sheaves that a person can take in 3 days, but despite that,
You haven't seen anything yet.
okay, so I'm going to give, so what I want to do is define D modules in just brutal generality. So on any pre-stack. Okay, so first of all, why is this a problem? Like, we've defined D modules on any pre-stack. It seems like Nick did that in his talk, didn't he? So the answer is no, he didn't. He only defined it on things of finite type. And we're dealing with things here of infinite type, like G of O. And it's a serious point, because if you deal with some infinite dimensional affine space, like, OK, you think on a usual smooth variety, it's you have an action of functions and vector fields. But on an infinite dimensional vector space, vector fields become like a pro-object. Like on infinite dimensional affine space, you think of that affine space as like a pro-object, and vector fields should be like the tangent space at 0, so that it's also a pro-object. And you will get confused if you...
In principle, it depends on any pre-stack.
Yes, so I will define it on any pre-stack.
No, it was defined already, but
No, only on finite type.
Where was it used?
but
It was used in finite type in the construction of D modules. So Dennis and Nick have some supposed book and they define IndCo on finite type schemes. So on finite type schemes, you say, I take bounded complexes of coherent sheaves with finite type cohomology. And if you did that in like on some arbitrary scheme, you wouldn't even get a DG category. It's not closed under cones. Yeah.
I think the objection that people are raising in my talk, it was actually defined as quasi-co on the Jerome spec, which makes sense for anything, but is not reasonable.
Yes. Yeah. So I just have no idea how to use that thing, and yeah.
It's
Okay.
not the
So
right answer.
yeah, it's not the right answer. Like you know it well. So.
And did we say what is a pro object?
What is a pro object? It's you think of it as a formal compatible system of things under maps that look like, well, when I say
We should know what is in the object.
it's ind object, but in the other direction. Yeah.
So is this like some compatibility with limits? So would it be easy to define on ind objects and hard on easy on pro objects, hard on ind objects?
Okay. I'm also.
If we use Nick's definition, would it be right on pro object?
It would no. Nick's definition is correct on things locally a finite type, and that's it. Yeah, absolutely. So, okay, so now here's a definition. So we have one approach to solving all of these problems. So first we have to define it. So what I'm going to do is I will define, let me say very carefully. So the first thing I'm going to do is define d of y for any pre-stack. And it will be contravariant. In other words, you'll only have upper Schriek functors. The question of like push forward is a more, I mean, let me just say it's a more subtle thing. We'll discuss it to some extent.
But can you just say?
I'll say in one pass what.
Model for infinite dimensional Frank space. What do you want?
I promise it'll happen in like a second. Yeah, I'll say something formal and then it'll be an immediate corollary, but it's just faster this way. So, okay, so we know at this point what we have to do. So first we have to give a functor d out of affine schemes. And let me just make my life a little easier. I'll only deal with classical affine schemes, because as we know, D modules only depend on the underlying classical scheme. So I need to define a functor d out of here. And where should we go? Certainly to the world of co-complete DG categories under continuous functors. So what's my definition? Well, if I have some random scheme S equals spec A, then I can write A as some colimit AI, where the AIs are finite type algebras. In fact, I don't even need to write colimit. I can just write it's the union of some finite type algebras over K. Just, well, everyone knows how to do it. A fancier categorical way of saying this is that, affine schemes classical is the pro category of affine schemes that are finite type classical. Everything is going to be classical. I might just suppress the notion. I'm saying classical because this isn't true in the derived sense. Like I'm really just writing A as the union of some algebras and like take finitely many elements, take the algebra they generate. That's something I only know how to do classically. So our definition, so we know what D is on finite type schemes. So first we'll define D from affine schemes. Well, okay, convention, everything is now classical. We're defining D from here to here. So we'll define it as the left con extension of D from affine schemes of finite type up. So as an example, so if I define A infinity, So the term, I should say, proviso, the term infinite dimensional affine space and this notation is ambiguous. There's pro-infinite dimensional affine space and in infinite dimensional affine space, and no one has developed good notation for distinguishing these two things, and it would be a great invention in mathematics if someone did. So this is here, by definition, the spectrum of an infinite polynomial algebra. So I can write this as the projective limit of ANs, which is just a way of saying that this A infinity, well, this infinite dimensional polynomial algebra is the union of the polynomial algebras on the first n generators over all n. And what that's telling me is that if I want to say what D modules on infinite dimensional affine space are, this is the co-limit of the categories D of AN. Co-limit in DGCat. So a priori, we're really worried about working with co-limits of DG categories because it's something very inexplicit. But note that in this case, our upper Schriek functors actually admit right adjoints because all of our structure maps are smooth. But those right adjoints are a little weird. They're shifted de Rham cohomology. So it's the limit under shifted de Rham cohomology functors also. OK, so for example, in that case, for any scheme S, let's say, so still an affine scheme, so it won't be so relevant, I can make sense of omega S as an object of, as a D module on S. Namely, I have some map from S to spec K, and it's just the upper Schriek of K. In particular, that makes sense for this infinite dimensional affine space. But if you try to think out in classical terms what it is, it lives in cohomological dimension, in cohomological degree minus infinity. Because, well, for AN, it lives in cohomological degree minus 2n, set n equal to infinity. Exactly, right. So it's, you can also think in terms of these shifted push forwards, but it's shifted push forward to AN. Well, if you were really thinking in those terms, it's like shifted by infinity, but different infinities for each one. But that's why that's part of the reason why it's not something that's really been considered before. OK, so OK, so now for arbitrary pre-stack. Yeah, I mean, you have to be kind of careful with the T structures here. So in this case, you presumably can construct the T structure because these upper, because, OK. I make no claims about T structures. OK, so for a general thing, we can, well, I'll define it as the right Kohn extension. In general, well, no. On A infinity, I'm sure there is, yeah. And yeah, there is, and you can describe it in very classical terms. Yeah, so in fact, well, in more generality than A infinity. So you can define it as the right Kohn extension. So what that says is that if you have some random pre-stack y, so let me just write concretely, where this term should be interpreted loosely, if someone gives you some random pre-stack y, then part of like what this categorical formalism tells you is that you can write it as the co-limit of some affine schemes. And now we're saying that d of y is equal to the limit of d on each of these SIs. No, because we've defined it on infinite type now.
But
SI is only assumed to be an affine scheme. So in order to compute this thing concretely, you have to first take your pre-stack as some colimit, then you have to take each term of that colimit, take its algebra of functions, write each one of those as a union. So you first take the colimit over those, and then the limit. It's a two-step process. And one is a colimit, and one is a limit.
you can't do it in one step.
You can't do it in one step, because they're different. Sorry? No, in both cases. So let me kind of try and give an example. Yes, that was the example I was going to propose. Okay, so one thing I can do is I can take a infinity infinity, which is supposed to be the colimit of maps. Well, let me write colimit under n's of a infinity, where each map a infinity to a infinity on coordinates is like x1 up to x1, x2, etc. Should be going to 0, comma x1, x2, etc. So you can think about this space concretely as spoof of k. Sometimes people write it like this, dot, 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 x minus 1, x0, x1, and then bracket here. So you're allowed in your polynomials infinitely many terms with negative coefficients and only finitely many terms with positive coefficients.
Sorry, this is the definition for
This is the definition, yeah. So it's what this right con extension phrase means.
So just one limit, but for a infinity we needed two limits.
Right?
I mean, we needed to do it twice.
For our earlier a infinity?
For the previous example.
For the previous example, no, we only needed to do, oh, it was both a colimit and a limit in that case. So
in that case, this definition seems not to work.
No, because I could have just called it the colimit and been done. But I was kind and said, aha, but not only is it a colimit, but it's also a limit. It's a second description, which is different, but not different, but it's not to say that you have to perform each process. You only have to perform one process at a time, but luckily either one is available to you.
And are you using some sort of statement like these stacks are always limits to colimits?
It's true for any ionadic category of something. Every object is a colimit of objects from the underlying category.
And the reason is that it's classified by an object is determined by the functor on finite by values.
No, so you mean for a general pre-stack? It's not. So for like an infinite type affine scheme, it's not determined by.
But it is determined by colimits, by values on colimits.
Yeah, something like that. By values on colimits of finite type algebras. Yeah. So what I'm saying is that the category of pre-stacks is, okay, not ind, but like pre-sheaves on a pro category. So it's sort of not ind, but kind of like ind of pro of finite type affine schemes. And I'm applying one thing for the pro and one thing for the ind. Okay, right. So I was trying to give some kind of example. And in this case, what the definition says is that, so for each one of these a infinities, I now know what the category of D modules is. And what I'm supposed to picture is that I'm embedding my a infinities larger and larger, one into the other. And now a D module on a infinity comma infinity is a compatible system of D modules on each one of these spaces. where the notation maybe is kind of bad, but well, I could give these indices and think what's going on. So a clearer way to say what's going on here is that before dealing with this worst kind of infinite dimensional affine space, let's deal with each kind of infinite dimensional affine space separately. So the first kind we've already dealt with. So the union of infinite dimensional affine spaces under embeddings is an end scheme of infinite type. It's the affine Grassmannian for GA. So we've talked about D-modules on the affine Grassmannian. And in this particular case, we said D-modules should be compatible systems on each of those finite dimensional subschemes. Then we dealt with the pro-infinite dimensional affine space. And we said it's the co-limit. So you think kind of, well, it's generated under co-limits by things pulled back from some finite dimensional affine space. And in the general case, it's some amalgamation with some order forced by necessity. Necessity.
I think the difference between two directions is that in one direction is kind of conjecture, so you have to use homological shifts all the time, and in the other direction is called the day, so there are no homological shifts.
Pretty much.
And this is basically the main difference.
Kind of, yeah. I mean,
So the first direction you
Imagine a typical object of this scheme.
yeah. So let me. We'll talk a little bit more about them, but let me say. Yeah, let me address that question a little more clearly in a few minutes. Yeah.
This for limiting that concretely, that's not filtered, right?
It is filtered. Oh, wait, this colimit? No, it's not filtered. Yeah.
So is it accurate to say that when you're taking the first limit, you get, if you start with affine schemes, the first limit gives you still affine schemes, and the second limit gives you.
Wait, sorry, I'm actually losing my mind. It is filtered, because it's just the you're no. Okay, I lost my mind. Yeah, it's not filtered. Okay. Yes. What was the question?
But in this second example, you can't write your I infinity infinity as a colimit of
Some schemes. Yeah, I just did it. So for any choice like this I choose, the answer will be correct. So I chose one way of doing it. I feel like I'm not addressing your question, so maybe you could.
So here I is not a finite type.
Right. No one says it has to be. So so the two-step process here is first do it for infinite type schemes, and then do it for sort of infinite type prestacks.
And so what's the answer for infinite type schemes?
The answer is take your scheme. It's spec A, right? Write it as a union of finite dimensional subalgebras. And now the category is the co-limit under Schriek pullback functors of D-modules on the spectrum of each of those algebras. So just typical formal object is the pullback of some D-module on one of those guys. And the x's between them are sort of whatever is forced on you by the x's coming from your larger subalgebras. Other questions? So another example. Yeah.
Is it obvious to find an example now for which taking quasi-co of x ram would not correspond to this definition?
I'm like 100% sure that if you did it for infinite dimensional affine space, you would get the wrong answer. I would just be kind of hard pressed to do it, the computation of the board. Like, the thing is, the formal completion of 0 inside of A infinity is hard to work with, and they're inside of pro A infinity is hard to work with. There are competing definitions, and I want to say A infinity de Rham should be the quotient by that, but I don't even know what the formal completion is necessarily, and whatever definitions I have, I can't really work with, and any of them that I try and work with, I get the wrong answer. So. Okay, so that's a definition. So there are some. So I need, okay, a couple comments.
You said you do another
Let me put off the example for a little bit. OK, so comment one of them is that it satisfies nice descent properties, so sort of FPPF descent. And a second comment is a little more serious. So it says that we have some push forward functor sometimes. And here's the specific claim. So let's be in the setting of schemes. OK, so setting will be classical schemes that are quasi-compact and quasi-separated. So the claim is that if F is a map between two such schemes, and it's what's called finite presentation, so you can basically think finite type, but one proviso, if it's a closed embedding, then you want the ideal to be cut out by finitely many generators, whereas obviously any closed embedding is a finite type map. Then there is a nice push forward functor, which I'm just going to call F star Duram. And nice here means commutes with base change. And also, it should coincide with the usual Duram cohomology in the case when S and T are themselves finite type schemes. So let's say S and T are affine. So I want to explain how to construct this. So if S and T are affine, then I can take my map from S to T. OK, what does it mean that so let's say S is spec A. So let's say that S is equal to spec A, and it's mapping to T, which is spec B. So what it means that it's finite presentation is that B is equal to A join x1 up to xn mod some finite set of polynomials with coefficients in A. Maybe, yeah. It means I can write it like this. So take all of the coefficients of all of my finitely many polynomials. Those all lie in some algebra, some subalgebra of B, and just take that subalgebra. It gives me some finitely generated subalgebra of B, such that I can make sense of this formula still. So everything is classical. Because we're doing D modules, I don't need to worry. So I can totally descend. What that says is that I can find finite type schemes like this, affine schemes like this, such that this diagram is Cartesian. And again, classically Cartesian. And moreover, actually, I could even sort of do better. I could keep increasing my algebra, like B prime, so that it better and better approximated my algebra, who's T? B. So if I wanted to find the push forward functor here, what do? So a typical, the fact that D modules on S are the colimit means a typical object is pulled back from this S prime. And if I want to compute the functor pull back push forward, by definition, this is going to be the functor, how does it work? Q upper shriek, F prime, lower star, Duram. And in fact, if I make this definition systematically for every such Cartesian diagram, I get a well-defined functor just by this formalism of colimits of categories. So this is meant to be a little bit of a heuristic for the idea, like why do I need finite presentation here? The answer is because all I know is finite type things, and this lets me descend to the finite type case. There was a question. Sorry? It's okay? Okay, and there's a claim, which is that in general, you can do this for any morphism of schemes of finite presentation. For general pre-stacks, oh, and actually, let me say some nice properties. So one of them is that f lower star Duram is left adjoint to f upper shriek for f proper and finite presentation. Yeah. At 4. What? Oh, wow.
I think you've covered everything.
Pretty much.
Depends what you want.
Oh, the equivariant.
There's the equivariant setting, but so I didn't say group actions on categories. People, okay, can kind of imagine. So.
We don't need those, right? So we only use
The particular case of G of K mod G of O mod G of O, basically.
let's
Well, we have to resign no matter what, right?
yeah.
No. Yeah. No. Well,
Is there holonomic?
there's holonomic. But it's a little more subtle than usual, so.